Hello everyone. We're going to discuss completing the square with inverse trig integrals. As you can recall, the basic inverse trig integrals were arctan u plus c. Notice that there's a 1 plus u squared in the denominator. Arcsin u plus c. There's a square root of 1 minus u squared in the denominator of the integrand there. And arcsecant u plus c, which is u times the square root of u squared minus 1. Let's take a look at example number 1. The integral of dx over x squared minus 6x plus 18. We would try various u substitutions, and if we had set u equal to the entire denominator, we can see that its derivative would require an x in the numerator, and we do not have that here. So our goal is to fit this into one of the inverse trig integrals. Which one is it closest to? Yes, it does look like arctan u plus c because there is no square root. The other two integrals, arcsin and arcsecant, have a square root in the denominator. So our goal is to represent this denominator as a number plus something squared. And whether this number is 1 or not, we could always factor it out so we could get the 1 that's required in the arctan integral. And this process that we need to use is called completing the square. So let's review how to complete the square for this trinomial. Our goal is to take the denominator x squared minus 6x plus 18 and rewrite it as a perfect square plus a number. So the trick is to add and subtract the same number so that the first piece will become a perfect square. Do you know what that number is? That number is 9. So we're going to add and subtract 9. And the way we get 9 is by taking the linear coefficient, and the linear coefficient here is -6. And we're going to take that, divide it by 2, and square it. So we're going to take -6, divide by 2, and square. That gives us -3 squared, which gives us 9. This procedure will always enable us to complete the square for trinomial as long as the coefficient of the quadratic term is 1. So now our trinomial can be written as x minus 3 squared plus 9. Before we get back to the integral, let's look at the geometric representation for completing the square. Let's take a look at this diagram. So we take x squared plus bx, which is represented geometrically in this first diagram here, right? And we have a rectangle x by x plus b. Now to complete the square, we take this rectangle right here, this one right here, and we divide it in half, which is indicated over here. And now its side is b over 2 by x. So we take the other half of that rectangle and insert it on the bottom so that we could kind of complete the rectangle and make it into a square with sides x plus b over 2 by x plus b over 2. But if you notice, there's a little square down here which has sides of b over 2 by b over 2. So to complete the square, we have to add a little square which has dimensions b over 2 by b over 2, or b over 2 squared. This is why the algebraic procedure works. So going back to our integral, the integral of dx over x squared minus 6x plus 18 can be rewritten as, in that complete the square form, x minus 3 squared plus 9. The only problem is that this 9 here has to become a 1 in order to use our integral. That is to say, it has to become the form of du over u squared plus 1 for it to be our arctan integral. So we factor out the 9, which is indicated over here. And of course, to get the expression back, we have to divide the x minus 3 squared by 9, and then, of course, divide 9 by 9, which is 1. And now we could, of course, factor the 1/9 out of the integrand. From here, we go on to u substitution. So trying to fit this into the arctan integral, we see that u squared is x minus 3 squared over 9, which would make u x minus 3 over 3. The derivative of that is 1/3 dx. Remember, x minus 3 over 3 is the same as 1/3 x minus 1. In fact, I'm going to write it over here, 1/3 x minus 1. And that's why its derivative is just a third. Therefore, 3 du is equal to dx. So let's try substituting. Notice that the dx becomes 3 du, and that, of course, could be factored out with the 1/9, and the coefficient becomes a third. So now our integral is 1/3 arctan u plus c, or 1/3 arctan x minus 3 over 3 plus c, which completes the problem. Let's look at another example. The integral of dx over the square root of negative 1x squared minus 8x minus 12. Which inverse trig integral is this closest to? It looks like it's arcsin u plus c. And what gives it away is that there's a square root in the denominator. There's no variable outside the radical sign to make it look like arcsecant. And the fact that we're subtracting something squared would make the quadratic coefficient negative. So that's why we would think that this is closest to arcsin u, except that we have to express the denominator in the form of a number minus something squared. So let's see how we could complete the square here. So if we rewrite the integrand as negative 1x squared minus 8x minus 12, notice that the quadratic coefficient is not 1, and in order to complete the square, the quadratic coefficient should be 1. So let's factor out a negative 1 just from the quadratic and linear term. So now we have negative 1 times x squared plus 8x, and the minus 12 will be at the end. So now let's complete the square here. So to complete the square, we divide 8 by 2 and square it. That would give us 16. So we would have to add 16 to make this quadratic a perfect square. However, what we really did is we added negative 16. So to make the expression equivalent to the original, since we added negative 16, we'll add 16 back so that we are subtracting and adding the same number and not changing this expression. In that case, we have just completed the square, and it has become negative 1 x plus 4 squared plus 4, which by the commutative property of addition, we could rewrite this as 4 minus x plus 4 squared, which completes what we were looking for. That is a number minus something squared. So now our integrand can be written as 4 minus quantity x plus 4 squared, which is closer to our arcsin integral. However, as in arctan, we need a 1. So what we'll do is we'll factor out a 4 within the integrand. So let's do that. And just like arctan, we have to divide each term by 4, whatever we factored out. So that leaves us with 1 minus quantity x plus 4 squared divided by 4. Now, if we factor out this 4, notice that it's under the radical sign. And there's a property of radicals that says that the square root of a times b is equal to the square root of a times the square root of b. So because arcsin has a square root in the denominator, we will be factoring out the square root of 4 in the denominator. So this is what we have. So now when we factor out the square root of 4, we're really factoring out 1/2. Don't forget that the square root of 4 is still in the denominator, and the numerator has a coefficient of 1. So 1/2 goes outside the integral, and we use u substitution as before, as follows. So now we set u squared to x plus 4 squared over 4. Our u is the square root of that, and our du is 1/2 dx, or twice du equals dx. Now let's substitute into our integral. So when we substitute our u into the integral, the numerator becomes 2 du, and the denominator becomes the square root of 1 minus u squared. The 1/2 times 2 becomes 1, and our integral is exactly arcsin u plus c, or arcsin x plus 4 over 2 plus c. The last problem I wanted to do with you is another arcsin integral, but what's difficult about this is just the algebra. Notice that the coefficient of the quadratic term is not only negative, but it's also not equal to a -1. We have a -4 there. So let's review how to complete the square so we could get it into that arcsin form. Okay, so we take our quadratic, -4x squared minus 12x plus 7, and separate the quadratic and the linear term as so, and we add the 7 at the end. Now, we cannot complete the square until the quadratic term has a coefficient of 1, so we'll factor out a -4. If we factor out the -4 from the first two terms, we get -4 times x squared plus 3x, and the 7 is there at the end. So our goal is to complete the square here. So again, we're going to add and subtract a special number, and here, if we take 3 and divide it by 2 and square it, it looks like we have to add 9/4 within this parentheses to complete the square. However, what we really did is we added -4 times 9/4. -4 times 9/4 is really -9. So because we added -9, we're going to add 9 back to get the original expression equivalent to this new expression. So now, because in our arcsin integral, recall that it's in the form of du over the square root of 1 minus u squared, we want the quantity to be squared. We don't want a coefficient. So what we'll do is, excuse me, we're going to distribute just the 4 and leave the negative outside. So if we do that, we get 4x squared plus 12x plus 9, which is really just 2x plus 3 squared. This minus sign is very important because we want it to express it in the form of a number minus something squared. And this is what we have, 16 minus 2x plus 3 squared. Now we should all be able to complete the square. Try it yourself. I hope the answer checked with yours. If not, everything is written out here. Have a great day and thank you for watching.